So the next topic is invariance with respect to the some rotation of axis. So what is an invariant mean? An invariant is basically an observable of a physical system which remain unchanged under some transformation. That means that you can say that the vector or the vector point function we taken in some case, so that is invariant with respect to the rotation of the axis. That means if we have some, you can say that this is some axis x1, x2 and x3. So, and this is the origin here, and here is some point P in the x1, x2 and x3. So I am taking another system, like you can say that another system, and I am going to check whether this is the rotation of the system. Like another system is a form like x1 dash, x2 dash and x3 dash. So this is the another system. This system is k dash, this system is k, and this is k dash system which has this origin O dash, and this k system has this origin, and this is the point P here. So these two axes are here. That means we are rotating this axis like this, and these are two systems. So what is an invariance mean? Invariance with respect to the rotation of the axis. That means if I am taking some vector field A in x1, x2 and x3 system, so that is equals to A dash, x1 dash, x2 dash and x3 dash. That means the position vector is same if I take this system or if I take this system. So this is basically the invariance. Now further is we are going to show some example, and we have to check whether the quantity is invariant under the rotation of the axis. So for this we have some example here that show that the quantity we have x1 square plus x2 square plus x3 square, that is equals to xi. Xi is invariant under a rotation of axis, you can say. So the solution of this example is we have to first let x1, x2 and x3 be the coordinates of the point, you can say be the coordinates of point P in the system, you can say K, like this. And x1 dash, x2 dash and x3 dash be the, you can say that be the coordinates of the same point, you can say that of the same point in the, now here the system is in the system K dash. Then we know that the transformation equations are, you can say that, then transformation equations are, so in this case we have two transformation equation, that xj dash, that is equals to lji xi, we discussed this thing earlier, and also xj dash, that is equals to L, J, K and xk. So these are the transformation equations. Now multiplying equation, this is called the equation 1 and this is called the equation 2. So I am multiplying these two equations. So that means we can write it as xj dash into xj dash, that is equals to lji xi into ljk xk. So that is equals to, multiplying this, we have Lji, Ljk, xi and xk. So further is this result, I can write it as del of I k into xi xk. We proved this thing earlier. So, and further is, now I am going to solve this thing. So if del of ik into xi, then that is equals to, or I can write it as in the form of the if this is same, so I can write it as xk like this. So, or I can write it as x1 dash. Now generally I am expanding this term, that is xj dash into xj dash, that is equals to xk into xk, or generally, or you can write it as del ik xk into xi, and this result is equals to xi. We took this result because we have this result here, that x1 square plus x2 square plus x3 square is equals to xi and xi. So I am taking this result. These two are same. So in the next step I can expand these terms. So I can write it as x1 into x1 dash plus x2 dash plus x3 dash, and that is equals to x1 plus x2 plus x3. So generally I can write it as x1 dash square plus x2 dash square plus x3 dash square, that is equals to x1 square plus x2 square plus x3 square. So this shows that the quantity, this one, that is x1 square plus x2 square plus x3 square, that is generally equals to xi. Xi is invariant with respect to the axis of with respect to the rotation of the axis. So this is the general proof here.